everybody. Welcome back to Mathematical Statistics. Welcome back from your one day off. I hope you used it wisely. You certainly earned it. But we are back, and today we are going to finish the 4 important tools for mathematical statistics. But first, I have a question in the chat about number 4 in the homework. So let me get my screen going here, and let's talk about it. Okay, number 4 is a transformation problem. We have a random variable x that has the exponential distribution with rate lambda. And we want to find the distribution of y equals x squared. And we want to name it, which is not always possible, but if I wrote that, that means it is possible. And it's going to be something on your table of distributions. So this is a function y equals g of x equals x squared. And I talked with a couple of you in my office hours yesterday about this not being invertible. So it turns out it won't matter, right? Because x is plus or minus the square root of y. But the x's here only take on values from 0 to infinity. So we can invert this by taking the positive square root over here. And that is what I'm going to do. So I'm going to write x is g inverse of y is the positive square root of y. So it's not invertible in general, but it is invertible in the right region for the support of x, so we're just fine. After this example, I'll show you what you can do if you are trying to find the distribution of a function like y equals x squared when your distribution can take on both positive and negative values, and therefore we really don't have invertibility. But continuing with this one, I'm going to write out the PDF for x. This is lambda e to the minus lambda x, and an indicator that says that x takes on values from 0 to infinity. I'm also going to write out the derivative with respect to y of g inverse of y. So up here I've got basically y to the 1/2, and when I take that derivative, I get 1/2 y to the negative 1/2. Okay, so we have a formula for the PDF for y in terms of the PDF for x. I am anti-formulas and memorizing formulas. I think you should probably just do this from scratch. And how we got this formula was looking at the CDF first, and you can do that here. This is one I don't mind us using just because you can derive it over and over and over again, and eventually you're just going to know it. So I don't know. I'm going to use the formula today, but if you don't know the formula and you're, taking a test or something, I would start with the CDF, the cumulative distribution function for y, and just go and you'll get the right answer. I have my PDF for x right here and the derivative of g inverse right here, so we are ready to go. I'm just going to plug this stuff in. This is lambda e to the minus lambda square root of y, indicator 0 to infinity square root of y, and then times the absolute value of the derivative, so times the absolute value of 1/2 y to the minus 1/2. Now we want to name this distribution, and the first thing I would always look at is the indicator to narrow down the possibilities. Like this is a function of y, and where does y live? I don't care where the square root of y lives, I care where y lives. I want to give the support or domain slightly different things for this function. So I'm going to look at the indicator, which says that the square root of y is between 0 and infinity. And if you just square things all the way across, this gives you that y is between 0 and infinity. So I can just change out this indicator for the indicator for just plain old y without the square root from 0 to infinity. And because y is going from 0 to infinity, I can drop these absolute values. And so again, that's because I know that y is positive. So let's rewrite this PDF for y. I've got this 1/2, so I'm going to just stick that here. 1/2 lambda e, sorry, I'm getting ahead of myself. 1/2 lambda, and then I'm going to put this y part here, y to the minus 1/2, e to the negative lambda, y to the minus, sorry, y to the positive 1/2. Yeah. And then an indicator, 0 to infinity of y. Just move this down a little bit. Okay, so can we name this distribution? I am seeing, just looking at the variables and ignoring the constants because they will have to work out right, I am seeing like y to a power and then e to the negative y to a power, which is almost looking like a gamma distribution where we have y to the alpha minus 1, e to the minus beta y, but the gamma distribution doesn't allow us to have a power on this y. So let's go to our table and start looking and see what we can come up with. I'm going to go to the continuous side because things are continuous here. And running down the table, I mean, you don't have to go through each one if you just see it, but like I know it's not this uniform distribution because that lives on a finite interval. Here it's from some alpha to some alpha plus beta, or you might see it as an alpha to beta or an A to B. There's many ways people write down the uniform distribution. And I know it's not the normal distribution. This doesn't have an indicator because this one goes from minus infinity to infinity, whereas the one we're trying to find only goes from 0 to infinity. For the exponential, we're on the right region, 0 to infinity, but our PDF is not quite complicated enough. So continuing in this way, I did say it looks almost like a gamma because we have like a y, the variable, to a power and an e to the minus y, but that one is to a power, which we don't have here. But look at the next one, the Weibull distribution. This looks maybe more complicated than we need, but like we don't have this minus alpha kind of thing going on, and we don't have an indicator from an alpha to infinity, or, do we? We have 0 to infinity. And if we take the alphas to be 0, which is allowed, if you look over here, the parameter space is not like it's usually alpha greater than 0, but here it's minus infinity to infinity. So it is okay to take alpha equals 0. Then I think we might have it. So let's go back to our actual PDF and see if we can match ours and conclude, hopefully, that we have a Weibull distribution when we square an exponential. I am going to remind you really quick over here. The Weibull distribution has 3 parameters. This is not a standard notation. I'm just going to write alpha, beta, and gamma. Those are our 3 parameters, but they could be in another order. They could be written completely differently. So this is not a standard, but if I write this, I think I'm going to mean the thing in the table, which is f of x equals gamma over beta, x minus alpha over beta to the gamma minus 1, e to the minus x minus alpha over beta to the gamma, and an indicator from alpha to infinity of x. So looking at the PDF at the top right of the screen right now and trying to match it to this, it appears that y has this Weibull distribution with, first of all, it looks like alpha equals 0. That will take care of our simpler looking things that we have in the Weibull distribution. And it will also take care of our indicator because our indicator goes from 0 to infinity. And if I plug in alpha equals 0 to the Weibull, we're going from 0 to infinity. So that looks good. As for the rest, we need to kind of massage it into the right form. I am going to just right over here, I'm going to look at the exponent right here on the e in our PDF for y. So this is minus lambda y to the 1/2. And I want to write it like this. So I want this to be minus y something to the 1/2. So it looks like y minus 0. And then to get that lambda, I need to have 1 over lambda squared in the denominator, because when you take that to the 1/2 power, you get 1 over lambda in the denominator, which flips up and becomes a lambda out front. So it does appear that my beta in the Weibull distribution, which is right here, is this denominator, is 1 over lambda squared, and my gamma, which is supposed to be this exponent here, is 1/2. I think we're done. Just a quick check. Um, if you plug in alpha equals 0 and beta equals 1 over lambda squared here, and gamma equals 1/2, this exponent will be 1/2 minus 1. So that is how you get the negative 1/2 on the variable out front, on the y. Yeah, and everything looks good. There's a gamma out front, and our gamma is 1/2, and it's right there. But you really don't have to check these. It might make you feel better to check these. But once you've matched up the functional part, the parts, not the non-constant part, then the rest has to be right. Assuming you did the transformation right, it would have to be a Weibull distribution. So I guess I finished the homework problem. Pretend you didn't see that though. But yeah, for number 4, starting with an exponential and looking at the distribution of x squared, we get a Weibull. And the fact that the function y equals x squared is non-invertible is not a problem because of the space we're working on. Does that make sense? Okay, so this, before I get started, this is not a homework problem, but what if we had to find, let's say we have x and it's continuous with a probability density function fx of x, and maybe y equals something like x squared. And suppose x can actually take on negative values. So we will have a problem inverting this function now. So that G inverse formula isn't going to work. So I'm going to write an expression. Let's find the PDF for y. And I don't have a distribution here, so I'm going to write in terms of the PDF for x. Our G inverse formula isn't going to work, but that doesn't mean we can't do the problem. We're going to take the same approach. When we proved the G inverse formula, we started with CDFs, and we eventually got to PDFs, and we put a formula in a box. So I'm going to do that here. I'm going to look at the CDF for y. This is a capital F sub y of y. This is the probability that y is less than or equal to little y. The only thing I know is that y equals x squared. So this is the probability that x squared is less than or equal to little y. And we know things about probabilities for x, but not for x squared. So let's kind of solve for x. This is the same thing as the probability that x is between the square root of y and the negative square root of y. Now I want to write this in terms of the CDF for x, and then take derivatives to ultimately get the PDF for y. And so note that this is the probability, right? I want the probability that I'm between these two numbers. So I want the probability I'm down here, and then I want to take away the probability I'm down here. In other words, this probability is the same thing as the probability that x is less than or equal to the square root of y, minus the probability that x is strictly less than the negative square root of y. So I see a CDF for x with the square root of y plugged in, and I almost see that here. Because things are continuous, I can, this is a strict inequality, but I can make it non-strict so that I truly do see a CDF for the second term as well. So because this is continuous, this is the probability that x is less than or equal to the square root of y minus the probability that x is less than or equal to the negative square root of y. If x were discrete, you couldn't do this step. You would have to address it differently, but I've got that the CDF for y is the CDF for x with the square root of y plugged in minus the CDF for x with the negative square root of y plugged in. So if I want an expression for the PDF for our new random variable y, which we got by squaring x, I would take the derivative with respect to y of the CDF of y, which means I'm going to take the derivative of this with respect to y. And when you take the derivative of the CDF, you get the PDF. So for the first term here, I get the PDF, the lowercase fx, square root of y, times the derivative of the inside. That's a y to the 1/2. So I'll get a 1/2 y to the negative 1/2, minus the derivative of this CDF for x is the PDF, evaluated at negative square root of y. And then I need to multiply by the derivative of this guy, which is negative 1/2 y to the negative 1/2. So we did it. We wrote the PDF for y in terms of the PDF for x. It didn't follow the nice G-inverse formula. That's a formula we put in a box to handle all the cases where it is nice and invertible and differentiable. But we can handle other cases. So one more time at the top here, if you're given a continuous random variable and you want to find the PDF for another random variable that is not exactly an invertible function, I would start with CDFs and just start writing out what you know and what it is and what you know and try to isolate the X. And the isolation of the X may be much more complicated than it is in this pretty simple example, but you should be able to do it in a lot of cases. So what can I clear up? Okay, then we are moving on. Let's get back to our 4 important tools for mathematical statistics. It's been a while, so number 1 in a circle in a box was what we just did. It was finding the distribution of a transformation of a one-dimensional random variable. We also talked about the discrete case there, so we had number 1 in a circle in a box, A and B, discrete case and continuous case. And then number 2 in a circle in a box was the bivariate transformation. So that's when we want to go from a joint PDF for an x1 and an x2 to a joint PDF for a y1 and a y2, where each of those y's is defined as a function of the x's. And we could easily generalize that to 3 x's and 3 y's, or 4 x's and 4 y's, or even n x's and n y's. And we actually used it last time to go from 2 x's to 1 y by renaming that y, y1, and defining another random variable y2, finding the joint PDF for y1 and y2, and then integrating out the unwanted random variable y2. So we are at 3 in a circle, in a box, and this is about minimums and maximums. So suppose that I am going to take a random sample from a distribution, and that means that I'm going to sample values independently, and that we're talking about one distribution. They are IID. They're independent and identically distributed. That's the same thing as saying random sample. So suppose, just as a setup here, x1, x2 out through xn has the distribution, and then I'm going to put an IID over it. And I don't know. I guess I'm going to start kind of generic. The example I want to use, so let me write something in here, is exponential with rate lambda, say. So these are random variables before they're observed. I don't know what they're going to be. And the randomness is based on the sampling, right? So although the exponential distribution is not a good PDF for height, if we assumed that the height of all students on campus follows an exponential distribution, which is silly, but just roll with it. We've got a PDF like this that's saying that a whole lot of area is here, not so much out here. So we're going to get more people with a height down towards 0 than we will up here, whatever up here means, because I have no scale. But if I were to sample n people, this represents the heights I will get when I do that sampling in the future. So they're still random. And when I do that, I will have n heights, and I will be able to look at the minimum of those n values. But right now, I haven't sampled those, so that minimum, I don't know what it's going to be. It could be, well, it's going to be a random variable itself. It's going to depend on what students were chosen from the population. So I want to talk about the minimum and the maximum as random variables themselves. Um, Another way you might think about this is like, I don't know, if you sampled these heights and got actual numbers and you collected a whole bunch of them and made a histogram, you should be seeing something following that exponent. That's so horrible, but something following that exponential PDF. And in this picture, I do have a minimum height, but if I throw that sample out and start over, I will get a different minimum. And if I start over, I will get another different minimum. And the minimum itself is a random variable with a distribution. So let's find the distribution or PDF or name it, I don't know, whatever it's going to say in your homework for y equals the minimum of x1 through xn. I'm going to start with CDFs because I have a continuous random variable here. And in fact, the formulas that we are coming up with today for number 3 in a circle in a box are only for continuous distributions. Discrete distributions would have to be treated quite differently because there could be ties, right? So if you sample something discrete and you get 3, 4, 1, 5, 1, you have the minimum of 1 appearing twice, and that has to be treated differently. And it's pretty ugly and something I would deal with on a case-by-case basis. So the minimums and maximums here are for continuous distributions, but the principle is the same. So you could maybe work this out for your favorite discrete distribution. For a continuous distribution, I don't have PDFs being probability, so we usually start with CDFs. I'm going to look at the CDF for y. This is the probability that y is less than or equal to little y. And all I know about y is that it is the minimum of x1 out through xn, and that has to be less than or equal to y. So I do know the distribution for each of the x's. Actually, in this computation, I'm going to keep it generic, and then I'll go back to the exponential distribution. So if I suppose we have a random sample, so x1 through xn, IID from a continuous distribution with some PDF fx and some CDF capital Fx, then to find the distribution of the minimum, what I want to do is rewrite this probability in terms of probabilities for the individual x's because that's what we know things about. We're given the distribution for the individual x's. So the goal, when there was just like one x and we looked at a transformation, was to kind of solve something here to isolate x and use what we know about x. And I'm going to do the same sort of thing here. I'm going to isolate the x's and use what we know about the x's. So let me draw a picture, a number line, and I'm just going to stick y, which is just a number, it's just an argument for this function on the number line. And let's ask ourselves, how does the sample need to fall, those n values, so that the minimum is below y? So it could be that like it's here and here and here and here and here. Like that's a sample of size 5. That's just an example where the minimum is below y. But we could have just like one here and then the others up here. And that's another example where the minimum is below y. And we actually could have them all below y. And that's another example where the minimum is below y. So this seems kind of complicated to get back to, what's going on in terms of the individual x's until you turn this probability around. So I'm going to look at the complement of this event. This is 1 minus the probability that the minimum of x1 out through xn, yeah, sorry, is greater than y. Because if I draw that number line again, there's only one way in terms of above and below that our sample can have a minimum above y. And that is if and only if each individual value is above y. So what I'm trying to say, going back to the left side here, is this is 1 minus the probability that x1 is greater than y, comma, which means and x2 is greater than y, comma, out through xn is greater than y. In other words, I rewrote the minimum probability in terms of what's going on with individual x's, and that was much easier to do once I looked at the complement of this event. Okay, so I've got a probability for x1, x2. This is the joint probability, and these random variables are IID. One of those I stands for independent. So by independence, this can be factored into a product of probabilities. The probability that x1 is greater than y times the probability that x2 is greater than y times out through the probability that xn is greater than y. Get rid of this up here. So that's by independence. And they're all identically distributed. So this is like 1 minus the CDF for x. I'm not putting an x1 there because there's just an x CDF or an x PDF, and they all have the same one of y. And this is the same thing because x2 uses the same CDF or same PDF as x1. And unlike some previous examples, I have the same argument for all of these. So all of those n probabilities are identical. So yeah, so by identicalness, this is 1 minus the probability that x1 is greater than y to the nth power. And if we want to write this in terms of the CDF for x, this is 1 minus the CDF for x evaluated at y to the nth power. So that is the CDF for y. And we can get the PDF for y by taking the derivative of the CDF for y with respect to y, and that is the derivative with respect to y of this whole expression here. So I get 0 minus, and then a little chain rule in here. I'm going to bring the n down, 1 minus capital F sub x of y to the n minus 1 times the derivative of what's inside, the derivative of just this stuff, which is 0 minus the lowercase fx. So the CDF for x, its derivative is the PDF for x of y. So I got a couple of negatives to cancel, but it looks like I've got n 1 minus capital Fx of y to the n minus 1 times lowercase fxy. The PDF for the minimum can be written in terms of the PDF and CDF for the individual x's in the random sample. So let's do it for the exponential, but I've already done more plugging into formulas than I'd like to do in one lecture. So let's just rederive this from scratch because it doesn't take long. Let's get a whole new board here. Suppose that x1, x2, out through xn are independent and identically distributed exponential random variables with rate lambda. So this means that we're working with the PDF for x, fxx is lambda e to the minus lambda x. I am being inconsistent again. You can certainly use an indicator here. You absolutely can use an indicator here, and it will end up in here. But I think maybe this is just easier to note that if you're letting y be the minimum of x1 through xn, then the support, like y, can take on any values that x can take on. So if all the x's are from 0 to infinity, y can be anywhere from 0 to infinity. It's likely closer to 0 because it's always the smallest one in a big group or some sized group, but there's no upper bound for y. So I think I'm going to leave the indicators off here, but you have to stick it on in the end when trying to name the distribution of this minimum. And yeah, that's what we want to do. So let's find the distribution of the minimum of x1 through xn. And I claim we can name it. Okay, so I've got the PDF for x. I also need the CDF. This is the integral from 0 to x of the PDF, so like a lambda e to the minus lambda u du. If you integrate this, you get 1 minus e to the minus lambda x, and that holds for x greater than 0. Okay, let's go. Let's pretend we didn't do that formula. The CDF for y, this is the probability that y is less than or equal to y. All I know about y is that it's the minimum of x1 out through xn, and that has to be less than or equal to y. Now, the game to play is how do I write this in terms of what's going on with the individual x's? If you throw a y on a number line, you realize that the x's can fall a lot of ways, to get the minimum below y. So this is a case where we turn this around and we write this as 1 minus the probability that the minimum of x1 through xn is greater than y. And then again with the number line, how do the individual x's have to fall so that the minimum x is greater than y? They all have to be greater than y. So this is 1 minus the probability that x1 is greater than y out through xn is greater than y. So my next two steps, you'll probably just write out in one step. But since it's our first time doing it, I'm going to say by independence, I get to factor these probabilities. Multiply. And then by identicalness, they're all the same. So this is 1 minus the probability that x1 is greater than y to the n. And we have the CDF for x up here, and that's the probability that x is less than or equal to x. This is, it's 1 minus the probability that x1 is less than or equal to y. So it's 1 minus e to the minus lambda y. So it's just e to the minus lambda y. So back over here, this is 1 minus e to the minus lambda y to the n. And when you raise something to a power and then to another power, you get to multiply the exponents. So let me recap that this is the CDF for y. This is 1 minus e to the minus n lambda y. To recognize the name of a distribution, we usually need to take a derivative because we're going to be much more familiar in this course with PDFs than CDFs. This one, though, I claim you can recognize it now because we just wrote down the CDF up above. It kind of looks like this, but with n lambda in place of lambda. But let's say we didn't recognize that because for the most part, you're going to have to take derivatives to get to something that is a PDF that then you can look up in the table. Okay, so when you take the derivative, you end up with positive n lambda e to the minus n lambda y. And keep in mind that y needs to be greater than 0 just because we reasoned that out at the beginning. The support of the minimum of the x's is the same as the support of the x's. And now maybe you see that exponential distribution. So our y, just to remind you, which is the minimum of x1 through xn, has, if you start with IID exponentials with rate lambda, has another exponential distribution. But the rate is now n times lambda. That's pretty cool. And it's not, I wouldn't say it's a usual thing that minimums or maximums have the same distribution that you originally started with, exponential to exponential. This one does, and it has a new rate parameter, and it's bigger than the old rate parameter. It's the old rate parameter multiplied by n, and that makes sense. So while I don't think you should intuitively expect an exponential distribution for the minimum, Given that it is an exponential distribution, you should expect that the new rate parameter is larger because our exponential PDF lambda e to the minus lambda x starts at lambda and goes down exponentially. And if we start higher up here, then, we can't just go down like this because this needs to integrate to 1. And so we have to actually come down much faster, to keep the total area the same. And so that means that there is more area down here towards 0 for the pink curve than the white curve. In other words, the minimum has a higher probability of being down towards 0 than the individual x's. Does that make sense? Okay. So yeah, the maximum is coming, but just when I started in my derivation of that formula, I regretted it right away, but I didn't want to stop. And that is, I regretted the chance to give you some notation for minimums and maximums. So let me slip that in now. If we have x1, x2 out through xn, IID, or maybe not, but for our class, it's always going to be IID. I am going to let x1 in parentheses denote the minimum. And then I'm going to let x2 in parentheses denote the next smallest, the second smallest, all the way up to x sub n in parentheses, which is going to be the maximum of x1 through xn. So this is a pretty standard notation. Another notation that you often see is x1 colon n, x2 colon n, down to xn colon n, which I kind of like a little better because it says the minimum out of what? Out of how many? So it always shows the out of n, but it's also a cumbersome thing to write. We're going to have subscripts and sub-subscripts, and so I'm going to go with this notation over here instead. And you'll see both around in the literature and textbooks and on the internet. And you can use either notation in your homework. I'll know what you mean. So if you're attached to that other notation for some reason, then by all means use it. But what we have shown here is that in our example, just to use this new notation, if x1 through xn is IID, exponential with rate lambda, then the minimum of the x's is exponential with rate n lambda. As with many of my examples so far, this is not just an example, but something we're going to need a lot of for this course. We're going to use this result over and over and over again. And so you'll probably have to show it several times until it sticks, because again, I'm not a fan of memorization. But eventually, you will have no choice but to just know that the minimum of exponentials is exponential and know what the new rate is. Okay? Okay, so we've got a maximum to talk about. Let's do it generically, as opposed to talking about the exponential distribution. So I've got x1, here's the setup, through xn, IID with common PDF f sub x of x and common CDF, cumulative distribution, capital F sub x of x. And I want to find the PDF for x sub n in parentheses, which is, we now know, defined to be the maximum of x1 through xn. Note that, even though the x1 through xn are IID, the x1 in parentheses through xn in parentheses, which are known as order statistics. A statistic is any function of the data, like taking the sample mean, that's a statistic. Adding up the data, the sum of the x's is a statistic. Finding the minimum or maximum or somewhere in between is also a statistic, and this has to do with ordering, so they're known as order statistics. So do you think the order statistics, now you have a new list of random variables, do you think the order statistics are IID? Your answer should be no, because the minimum is definitely smaller than the maximum, right? So not even knowing anything about the shape of the distribution, a PDF for a minimum is probably kind of piled up low, while a PDF for a maximum is maybe kind of piled up high, and it's got a different shape. It's not exactly the same PDF. So the order statistics are definitely not IID. They're definitely not independent. There's a lot of dependence there. The minimum has to be less than the second or next smallest. So not IID. But we're going to find the PDF for the maximum. So we're going to start with the CDF capital F sub X sub N in parentheses. I can give this any argument. I'm just going to write X. I mean, it's just an argument of a function. You could write X sub N in parentheses, but it's just an argument of a function. And so why drag around that mess? It's going to be messy enough. So I'm not going to do that. This is, by definition, the probability that the maximum is less than or equal to X. You don't have to do this next step, but because we just started seeing this notation, I'm going to write this a few times. This is the probability that the maximum, this is me just kind of unpacking that notation. I'm really not doing anything else. And now the idea is, if the maximum is less than or equal to X, what can we say about the individual X's? Let's look at a number line. How does the data or sample have to fall so that the maximum is less than or equal to X? Like it can't fall like this because the maximum would be above X. It has to be that all of the individual X's are below X. I'm using X's for way too many things. To get the maximum of a data set below this X, they all have to be below X. So in this case, we do not have to consider any sort of complement. If the maximum is below X, that is the same thing as saying that X1 is below X, comma, and X2 is below X, comma, and Xn is below X. Because they're independent, we'll stop doing this after today. I would just write IID and do this line and the next line all at once. But because they're independent, we get to multiply these probabilities. And then each one of these is the CDF for X. They're all evaluated at the same place. So these terms are all identical. What we have here is that this is the CDF for the original distribution X to the nth power. So to get the PDF for the maximum, we would take derivatives. And I'm going to take the derivative of this, and I'll get n times the CDF for X of X to the n minus 1 times the derivative of the inside, which is the PDF for X. So there is a formula in a wiggly box if you want a formula. But again, I would probably just do this. Writing these steps out was not a big deal. And it gives you some intuition, whereas a formula does maybe not give you any intuition. Let's do it for our exponential example. This one we actually won't be able to name. So it's not a nice known named distribution, but that doesn't mean we can't find the PDF. Right, so find the PDF for the maximum. I'm going to do it the long way because it's not that long. I'm going to start with the CDF. This is the probability. The maximum is less than or equal to X. If you need to, write it out. You don't have to do this. Max X1 through Xn is less than or equal to X. Draw a number line and realize the only way the maximum of the sample of size n could be less than or equal to X is if they're all less than or equal to X. So the first one and the second one and down to the last one. And now I'm going to do it all at once. Because these are IID, I get to factor this. And because they're, identically distributed, one of those i's says I get the same thing over and over again, so to the nth power. And so this is the CDF for that exponential, which we just saw is 1 minus e to the minus lambda x to the n. So I want to find the PDF, so I am going to take a derivative. The PDF for the maximum is the derivative of the CDF. In this case, I get n 1 minus e to the minus lambda x to the n minus 1 times the derivative of the inside, where I will get 0 minus, bringing down a negative lambda, plus lambda e to the minus lambda x. So let me just clean this up a little bit. And this holds for x greater than 0. I would say, and it's 0 otherwise, or maybe I would just take the whole thing aside. I'm not a fan of you like suddenly doing cases here when you were not doing cases above, because it's not really equal to the line above. But yeah, overall, I can write the maximum PDF as n 1 minus e to the minus lambda x to the n minus 1 lambda e to the minus lambda x times an indicator that says x is greater than 0, because the min and the max always live on the same space as the original x's. So we have found the PDF. This does not have a name, but if someone asked you maybe for, this would be horrible, but maybe for the expected value for this, you would just integrate minus infinity to infinity x times the PDF for the maximum. And then this PDF, I'm not going to do the integral. The limits of integration would cut off between 0 and infinity. Then we get x times n 1 minus e to the minus lambda x to the n minus 1 lambda e to the minus lambda x dx. And go. It's not nice. But again, if someone asks you for something involving the maximum, you probably have to find the PDF to compute the thing. Maybe. Certainly for an expectation. What if, just real quick, if we have x1 through xn, IID, exponential with rate lambda, and we want to know the expectation of the minimum, we could say that we know the minimum is exponential with rate and lambda. Go to your table. If it doesn't say work it out from scratch, certainly your table is valid. And figure out what this has to be. The expectation or mean for an exponential with rate lambda is 1 over lambda. So for an exponential with rate n lambda, it's 1 over n lambda. You don't have to go doing that from scratch unless I specifically ask for that in an exercise. Okay, so that's mins and maxes. We're going to be seeing them a lot and more tricks with them. We are not really concerned with the other order statistics in this class. You'll see why eventually. I am going to put together a separate video to deal with the other order statistics that is completely optional, recommended for the grad, people signed up for the grad section of this course, but even optional there. I think it's something you need to look at before you take the prelim, but you're not going to be tested on it in this course. So we're going to look at things like the PDF for the third smallest, as well as joint PDFs, maybe like a joint PDF for a min and a max. And a joint PDF for all of the order statistics. And look at what it means to, integrate that and get one. The limits of integration are going to be all like stacked, right? Because the minimum has to be less than the next one, less than the next one. So that's just going to be an optional video that I'll post for fun. But yeah, grad students, I don't know, bookmark that and come back to it before your prelim. We are here at number 4 in a circle in a box. This is the final thing in the list, the 4 important tools for mathematical statistics, at least what I think are the four most important tools. There's lots of important tools. And this is about moment generating functions, affectionately referred to as MGFs. I always put like an apostrophe to separate that. I know it's not like a possessive thing, but it's an abbreviation with an S after it. And I don't know, I feel like I need to separate that somehow. MGFs. Okay, before defining this, I want to define what a moment is for a random variable or a distribution. So let's put a definition right in here. Let X be a random variable with some distribution with a PDF. And it could be discrete or continuous. And if it's discrete, you might call it a PMF, but I call them all PDF. The moments for X, or more really for the distribution, are the expected value of X, the expected value of X squared, the expected value of X cubed. Can you see where I'm going with this? The expected value of X to the fourth, etc. Now, before you say I've seen moments and this is not it, let me qualify this statement. But this is the first moment. This is the second moment, etc. The third moment, the fourth moment. And so if you've seen moments before, you might have seen like a minus mu in here. So recall that we use mu to denote the mean of a distribution or a random variable. And moments can also be defined as the expected value of X minus mu, the expected value of X minus mu squared, the expected value of X minus mu cubed, and so on. We're not going to need these for a while, but these are called centralized moments, and these are technically non-centralized moments. We're just going to call them moments, and if we need to talk about these, we'll call them centralized moments. But I'm not going to spring that on you. I will define these if we're talking about these. So yeah, you may have seen moments defined either way, but there's actually two ways to define them. Some are centered around the mean and some are non-centered around the mean. Mu. So the moment generating function is something that can generate or compute these moments for us. I mean, we do know how to compute these. For example, the expected value of X to the fourth would be the integral or sum. Now, this definition is for discrete or continuous. So maybe the integral X to the fourth times the PDF for X dx. In the continuous case, or the sum over all X of X to the fourth times the PDF, which is just a probability in the discrete case. We do know how to compute any particular moment, but the moment generating function is a slicker way to do it that is sometimes easier, and yet we're not going to care about that. We're going to care about moment generating functions for a completely different reason, which is going to be amazing. So let me define the moment generating function. The moment generating function, or MGF, for X or for the distribution, is going to be denoted and defined by a capital M. Now, this is not 100% standard notation. So a capital N, M for moment, a sub X if necessary. I won't always put the subscript, but if we're talking about moment generating functions for two different random variables in the same, problem, you might want to use a subscript. It gets an argument that is generally not X. It's usually a T, like T, S, U, and V. Those are some of the more common letters, but it is an argument, and I guess you could put an X in there. And it is defined to be the expected value of e to the t capital X, which is looking pretty weird. Yeah. So we're going to see, probably not going to be until next time, how we can get moments out of this. And we're also going to see why we care about this beyond moments. But I think today, for part A, we can at least get into just finding, like just computing a moment generating function. You'll note in your table of distributions, the final column on both sides is a column of moment generating functions. So in your homework, you'll have a few exercises to find a moment generating function from scratch, not just to report it from the column, but you can look and make sure you've matched the moment generating function. Okay, we haven't done a discrete random variable in a long time, so let's do one, and we'll also do a continuous one. So suppose that X has the Poisson distribution with parameter lambda. We're so early in the semester, but I can't remember if we've talked about this. We might not have. This is a discrete distribution, and the probability that X equals some X is e to the minus lambda, lambda to the X over X factorial, and this lives on the discrete set 0, 1, 2 on up. So it can take on all non-negative integer values. So there's the probability mass function, or as I call it, the probability density function. And it's a distribution that's really useful for counting things, where you're not counting like like how many times out of n sounds more like a binomial distribution. But this will give you nice non-negative integer values, and it's huge in Markov processes, and we'll talk more about it here and its importance here, but for now it's just a PDF. So let's find the moment generating function for X, or for the Poisson distribution. So I'm just going to start writing this out. The moment generating function as a function of some like t, it's defined to be the expected value of e to the t capital X. And by the law of the unconscious statistician, I am just going to sum over all x, e to the t little x, times, for this discrete case, the probability that x equals little x. And the x's we're going to sum over are 0, 1, 2 on up. So this is the sum as x goes from 0 to infinity of e to the tx times e to the minus lambda, lambda to the x over x factorial. I know this notation, you might be confusing my lambdas and x's. I'm trying to be really careful about how I write this. Yeah, so let's add this up. We can sum without summing here. And I think the first thing I'm going to do is say that this e to the tx is really e to the t to the x. So I've got something to a power of x, and I've got something to the power of x over here. I'm going to rewrite this whole thing as the sum as x goes from 0 to infinity of e to the negative lambda, and then lambda e to the t all to the x. So that's from this lambda, and then this e to the t all to the x over x factorial. So to sum this up, you could pull this out, and you could say that you recognize like a Taylor or Maclaurin series expansion for an e. We could use the fact that like e to the x is the sum as n goes from 0 to infinity of x to the n over n factorial. But let's do it the math stat way. Let's do it by summing without summing. This summand over here looks like the Poisson probability mass function again. But in place of this lambda, we have this big mess. So I'd like to see that big mess up here as well. So I'm going to go for that. I'm going to write this as the sum as x goes from 0 to infinity. I'll leave myself some space here. Lambda e to the t to the x. And I'd like this to be e to the minus lambda e to the t over x factorial. And I can't just do that. That's not equal to the line above. To do that, I need to pull out the original e to the minus lambda from up here, and also put in an e to the positive lambda e to the t, which is going to cancel this one out. So that's how I get, this line equal to the line above. And now this is the PDF or PMF for the Poisson distribution with parameter lambda e to the t. So this is a function of t, but we're thinking of a fixed t. When you plug in a t, we're looking at summing over a lambda PDF with a constant parameter, and this whole thing sums to 1. So this whole thing is 1, and I'm just going to put these others together. We get e to the lambda e to the t minus 1. What t does this hold for? It holds for any t's for which this sum converges. So I've got like an e to the t in here, and a positive t is something positive, and a negative t is still something positive. E to a negative number is still something positive. And so I still have e to something negative, no matter what t is. In some cases, your moment generating function sums or integrals are going to diverge. They're not going to sum to something finite for certain t. So you do need to finish this off by saying, where can t be? And t could technically be negative. Let's go real quick. I have just a couple minutes left to the table of distributions and the discrete side. I am, again, on the discrete side. I'm going to go to the Poisson, over to the moment generating function column, and you can see what we got there. It's written as exp, which is just a way to write, e to the lambda e to the t minus 1 if you don't want to do superscript and another level of superscripts. And in the moment generating function column, you'll see that some of these have restrictions on t, but in this Poisson row, we do not have any restriction on t given for the moment generating function. So I am out of time. I was a little ambitious to finish the 4 tools for mathematical statistics. When we come back, I will do an example of finding a moment generating function for a continuous case, and then we'll go to part B, which is actually using it to find moments. And then we'll go to part C of 4 in a circle in a box, which is what I think the most important application of moment generating functions is. And it doesn't actually involve moments at all. So cliffhanger, I hope you come back. And I'll see you maybe in the next one. And I have an office hour now, so stick around. But if you don't have any questions, then bye.
This is oh no, oh no, oh no, oh no. Someone put the light on. I need you to. I also. I see you like squash. I wish you could. Everyone is. We're just trying to sleep under here.